So this will be an introduction where I'll also try and introduce some of the philosophy of Gaussian processes. Rich is going to follow on with us. We have a tradition doing two introductions because I always think when I was learning about Gaussian processes I had to see about 4 introductions before I even started to get the hang of it. So probably there's a lot more material. I mean there's great, my favorite is probably David Mackay's video online, which how many people have seen that? Or you've got to watch that. I should retweet it again. That's David sort of 11 years ago talking about Gaussian processes. So there's lots of other material, but I'll try and give you sort of my sort of twist on it, as also you can see me doing online. So this book, Gaussian Process for Machine Learning, is now incredibly 11 or 12 years old. I think it's still a very good introduction to the subject. And it's also freely available online. It's certainly, I mean, I didn't learn Gaussian processes this way because I was working on it at the time, but when they published this book, it was a big change in the accessibility of the methods. You saw suddenly an enormous increase in the number of publications on GPs, because up until then in machine learning, so I should say that's for machine learning, very few people were aware of them. Of course, in other subject areas, they're also worked on, like statistics, geostatistics. Okay, so I like to sort of cast things in the terms of why I think this is important or useful. And so the first thing I like to do is sort of go back to basics and answer the question, what is machine learning, or what it is to me. It can be anything you like to you. There's no rules on it. But for me, the important thing about machine learning is this, that you're trying to combine data with a model to make a prediction. Now that also is probably true of many other fields, including statistics and certain aspects of signal processing, and maybe even all of science. Because of course in science you're also sort of acquiring data, and you have a hypothesis and you make a prediction, and then the classical model of science, you then use that prediction to try and determine whether your model is correct or not. So it's a way of assessing the quality of your scientific model. But to me this is really important because you can't get away without the model. Now I'm also missing something here, which is the computation, the algorithmics. So which is just going in this sort of, that probably shouldn't be an equal, that should be a right arrow or something. The algorithmics, which is like, well, how do you combine your data and your model computationally? So you can actually easily dream up different models of the way data is generated, right? And if you think about the sort of thing people do with computers now, simulations, large-scale programs for simulating, those are all models, they're computational models. But they're often difficult to combine with data. So there are techniques like ABC, which Rich is actually expert on, where people attempt to do that. But the challenge is typically you want an efficient way of getting to your prediction. So that in large respects constrains the class of models that that you can actually use in practice. So you may like to use a very, very general set of models, but because you have to combine them together to form something else, what I would say is the algorithm for making your prediction, you end up perhaps using a more restricted class of models than you would actually like. Now I think my argument for why Gaussian processes are interesting is because they're actually a very broad class of models, relatively speaking, that allow you to make this combination somewhat analytically, not analytically in all cases. So that's very nice because they give you sort of non-linearity, they give you uncertainty, non-linearity in the function. They're sort of, well, they don't have parameters, but conceptually somehow they're linear in their parameters, which is why they're very easy to work with. The key aspect for me is this combination of data and the model. And that's why I think GPs are very interesting. Now there are another aspect, I should say a word probably about, dominant techniques in machine learning today, things like neural networks that everyone's very excited about. So of course that's the same thing. It's just in the neural network you have a model which is a sort of deep neural network or whatever. Now why is it still, those are very complex models actually. And they're actually quite easy to combine with large data algorithmically to make predictions. So that's why they're very successful, because with large data they're working very well to make predictions. So why are Gaussian processes interesting in that light? Well, one domain is because as a model, the Gaussian process is much more mathematically understandable. So it's mathematically simpler. So a lot of people are put off in the neural network world. If you come into machine learning or some domain like this for the first time, and then you see what the algorithm is for a neural network, it seems simple. Algorithmically, it seems simple. You can actually sort of, nowadays, with the software available, you can code them up very, very quickly. But mathematically, they're very, very complex. They're very hard to sort of say exactly what you're doing. People have instincts about them. They're very interesting models. Whereas mathematically, Gaussian processes are sort of relatively simple and easy to do theory on. And I'm not going to do a lot of that myself in this session, but I think it's an important reason. And I don't want to sort of say that one should use them. You know, I'm very keen on the idea that when you're doing machine learning or data science in practice, if you're trying to solve a problem, you know, it's not like football where you follow the team, you know, until their death. You do the method that's right for the circumstance. So sometimes the Gaussian process is the right thing to do, and you'll see it very widely used, for example, in hyperparameter optimization, because it is very much the right thing to do there. And sometimes it's very hard to use a Gaussian process. We'd like to be able to use Gaussian processes in these very large data sets of images and these sort of things, but they're not easy to deploy. And you know, we're working on that. We're interested in that. But if you're doing things in practice, sometimes you use something else. So, of course, data itself, there's just some definitions there. I mean, of course, it could be actively or passively acquired. And metadata is sort of interesting now. You see a lot of, you know, hyperparameter optimization is somehow learning about learning. And I think that we're going to see that increasingly. If you think of things like AutoML, where Gaussian processes are very widely used, people automating the process of machine learning, then the data is often metadata, data about the data sets. And the assumptions, the model contains your assumptions. So those assumptions are based on previous experience. That could be coming from other data. Transfer learning. Transfer learning is something that certainly I think a lot of people have done stuff with Gaussian processes. And if you model probabilistically, it's kind of clear the sort of things that you can do. And I think transfer learning is an area where there's a lot of room for improving the quality of what we're doing. So I think that the main thing it includes is really your beliefs about the regularities of the universe. But you kind of don't want to put too much of those beliefs in, because then you overwhelm the data. There's always this trade-off between letting the data speak and letting the model dominate. So in a classic mechanistic modeling framework where you write down a differential equation, typically you don't worry so much about the data because you know the physics and you're dominated by the model. In machine learning, you tend to write weak mechanism, like smoothness. So another sort of term for this is the inductive bias. So in machine learning, I think an interesting difference between machine learning and statistics is how people view this process. So philosophically, I think a machine learner is trying to make good predictions. They don't care so much about interpretation of the model. Whereas in statistics, people are typically trying to get a model that's interpretable somehow, so that you can go to the government and say, look, this decrease in the price of alcohol is causing heart disease, or an increase in the price of alcohol would reduce heart disease, or whatever else, because you're trying to get interpretation from it. So that means classically in statistics, the models tend to be less complicated in machine learning. The other thing in machine learning is I don't think that most machine learning researchers are that worried about introducing a bias into their model if it gives them good predictions. Because the sort of core idea of machine learning is to try and emulate human capabilities somehow. And we know that humans are biased. So, you know, one quote I've made is statistics are trying to turn humans into computers, and machine learning is trying to turn computers into humans. In that sense, because of course statistics is more worried about removing human bias, whereas machine learning is sort of like, hey, humans can do all this cool stuff. Why can't computers, with all their logic and rationality? Oh, we have to bring in assumptions and bias. So the great thing is, of course, that nowadays, certainly in Gaussian processes, there's a lot of interplay between the two fields and a lot of sharing of ideas. Who here is from a sort of stats background rather than a... So there you go, like 5, 6, 7. And machine learning would say, and something else. Good. Modeling, it's all modeling, right? Whatever it is, all science is somehow modeling. Okay. So I think, but I do think that these philosophical ideas are important, because I think if you don't take them into account, then it's harder to communicate with people in other fields. And right at this moment, I think machine learning and statistics deploying in certain domains. That's really, I think all the interesting stuff for me is going on between fields. I know everyone's going on about how we're going to solve AI and all these sort of things. But I think the most interesting things I see is where you're trying to apply these things in particular domains. Okay. So I'm going to start very basic because it's about Gaussian processes. And I'll start with the Gaussian density, which I'm presuming most people, all people, have seen before. You know, as I say often in this lecture, I hated the Gaussian density when I was at school and university. It just seemed like the most tedious piece of anything that you ever did, because all we ever did was we computed the mean of the density and then maybe the standard deviation. And like it didn't feel like real maths because we used to do it in maths. You had, okay, the mean formula was easy to remember, but the standard deviation wasn't so easy. I'm talking like when I was 13 or 12 or something. And then there were tables, and who liked tables, to look up like where the probability lied, right? It just seemed really uninteresting. So I think that the reason I've become personally convinced slightly, I'm not really convinced of anything because I'm Bayesian, so, but as much as convinced as I can be about anything, I kind of think that the biggest issue with Gaussian processes is the word Gaussian. That there's some sort of implicit bias against Gaussian. Every time you mention a Gaussian process to someone who hasn't seen them before, they come out with reasons why Gaussian isn't good. And then they mention another model, which doesn't have, so for example, they might say, oh, I'm going to use the Markov process because, because Gaussian, my data isn't Gaussian or something like that. But very often, it's fine to do that. It's fine to use a different model, and one should use different models. But what I notice is that people don't understand the richness of this class of models. They often will tell you that I'm not using a Gaussian process, my data is not Gaussian, I'm going to use a Kalman filter. It's like, okay, that's a Gaussian process. I'm going to use a basis function model. Okay, that's a Gaussian process. So many models that people use are Gaussian processes, but because they don't have the word Gaussian in them, people seem to like to use them. And very often it's the right thing to do as well. It's not necessarily the case. We're going to introduce the Gaussian process in the most general way. So you define a covariance function and then you use linear algebra to try and do your resolution of to fit your model. And it's not always the case that you want to do that because algorithmically it's slow, because that was the thing missing from my earlier plot, right? The sort of how you go to the data. The combination of the data plus the model, you need an algorithm to do that, and that has some computational hit. And the most general form of a Gaussian process is cubic in the number of data, as we'll see, and quadratic in storage, cubic computationally and quadratic in storage. So very often that's the reason why you don't use a Gaussian process when you're doing some sort of regression problem, because of that sort of hit. So, okay, there it is, and I've sort of indicated the mean there. I sort of really like the fact that it's often used to introduce heights because, of course, it has mass in the negative domain, so you shouldn't really use it for distribution of heights. But it's actually, in some way, it's also okay to use it in the positive domain because its tails go down so quickly that the probability of seeing anything down here is absolutely zero. You're never going to see anything down this far away. As you start getting not absolutely zero, it's not zero, it's got support everywhere. So it's got support everywhere, but these probabilities get really small very quickly because of this squared exponential decay, exponentially quadratic decay. So that because these numbers are going up here as the square of the distance between the mean and y, and then this is being e to the minus that square, those things go to zero relatively quickly compared to some other distributions. So it's not considered light-tailed because to be light-tailed you have to have less tails than the Gaussian. But it is true that it's not, if you've got sort of high noise on this, you get very nasty effects. If you get sort of like large outliers, then the Gaussian's very sensitive to outliers. Okay. So the funny thing about the Gaussian is that I think we get taught this quite early on, is it has these important properties, the first of which is extremely, well, it seems very unusual. You can't count the number of distributions because there must be continuously infinite number of them, the total number. But the number of distributions we know, only a few have this property that if you add the random variables, so if you take samples from the distribution and then you add the variables together, then you stay in the same family. So the Gaussian has this interesting property that when you sample a bunch of y's from the Gaussian and you want to know the distribution of the sum is drawn from another Gaussian with the mean being the sum of the means and the variance being the sum of the variance. And in some sense, it's this fact that makes it so useful. Because, as we'll see, and Philip Hennig, who did the second introduction on one of these schools, did a really nice job in that introduction. You can find these all online, these videos, of emphasizing the fact that working with Gaussian processes is like playing with linear algebra, right? So linear algebra we know how to do, and manipulation of Gaussian processes, because of facts like this, turns out to be very similar to linear algebra. We'll see that when I look at the multivariate Gaussian in a bit. So the mean sums, that's not that surprising, but the variance is also sum. So that's the important point, that as you increase the amount of data, you sum the variances. But notice the standard deviations don't sum. So of course, if you sum a large number of values, then you take the square root of this whole thing to get the standard deviation of the result. It's not the sum of all the standard deviations. If the standard deviations were to sum, as you will observe more and more, you wouldn't lose on the scale on with your axis of what you're looking at. You wouldn't lose any uncertainty in the standard deviation. But because the variance is sum, as you take the square root at the end, the standard deviation of this sum is much smaller than the sum of the standard deviations. Okay, then the other one is scaling the Gaussian, and this is perhaps less unusual. It's quite common to find a situation like this, where you scaling a density simply leads to the same density. So many densities scale. So that's not that uncommon. Not many densities sum, but many densities scale. So that's another thing. And those two are going to be important when we go multivariate later. Okay, so so what we're going to try and do and start introducing the Gaussian process for is for dealing with functions. And the classic example is regression. So here's some examples. These are old examples of regression that I sort of use, where you're trying to predict a real value given some inputs x. So there's some really an old example is predict the quality of meat given spectral measurement. That's an interesting one. Actually, at Amazon, there's work where people are predicting the quality of fruit given spectral measurements of the fruit for Amazon Fresh, which is very cool. That's kind of a little bit like a regression problem. Radiocarbon dating is a classic example that people did a lot of work on around here in Sheffield. So the C14 calibration curve. So the C14, you do radiocarbon dating, you look at the amount of radioactive C14 isotope in your sample, and then you try and calibrate that, making an assumption about the C14 being constant in the atmosphere across all time, which it hasn't been. So what they do is they can do a regression. You can know the actual data samples from these tree ring surveys. So you can get tree rings, and of course trees have carbon in them, so you can radiocarbon date the tree, but then you line up all these trees because the tree rings have this special pattern because summers and winters vary, particularly in Sheffield. And so you get different size of rings around the summer and winter according to the quality of those times. You can map them up, and so you've got a ground truth that people then use to calibrate the C14 isotope. Now this is old. People originally looked at Go, so that's sort of been solved now, kind of, with a large neural network. But people used to look at these things and use regression for predicting the quality of moves. And in very old work, also backgammon. So scoring moves by experts would rate how good a move is to try and extract information. Kind of difficult to do. But the little example that I like to look at is this one. So pace times for the Olympics. This is a guy called Stephen Kiprotich who won the 2012 Olympics. There's only 2 Ugandan gold medals, and that's one of them. So that was pretty special, and I gave this talk in Uganda once, which is why I have Stephen Kiprotich here. So the reason I like this data is because it's sort of, I mean, it's small, so you can play with it, but it has interesting characteristics. So in 1904, they got lost, and they did a marathon in like, I can't run a marathon that fast personally, but I almost can. I think I'm up here. So they got lost and they got covered in dust. So that's an outlier. That was in the United States, St. Louis. I can't even run a kilometer that fast. I mean, it's it's just absolutely shocking how fast these guys run. Alan Turing, by the way, does anyone know what his marathon time was? No? 2 hours, 47 minutes. He's fast. So he would have, that was in the 1940s, and I think that would have placed him just about here. He would have come about 10th in the Olympic marathon or something like that, well, 15th in the Olympic marathon if he had run it in that year. He was really fast. That 2 hour 47 marathon is very fast today. You know, people trying to break 3 hours. That's how you get into Boston. You break 3 hours, and not many people do it. And that was like before any idea about training. It's extraordinarily fast. Okay. So, and I think that a lot of us have seen formulas like this. So the data we have is given by some inputs, and we might want to predict the marathon time, pace, as a function of the year multiplied by some gradient and some offset. That's the classic sort of thing we used to do. I don't know when people do that nowadays. I think, again, I did that around the age of 13 or something. You used to have to do it in physics. So that's what this looks like. And what I think is interesting is to go back and think what it meant when people first started doing this. So the early people who tried to fit curves to data were sort of these mathematician astronomers, sort of around the late 18th century, early 19th century. People started, they had very good instruments for mapping the way, a lot of planets were discovered around then. And they wanted to fit curves to data. Now, something that I think is always worth remembering, because you never get taught this when you get taught about line fitting, because it's not the simple way to teach it. But I think it's important if you're going to go more complex with machine learning. So, I mean, of course, you only need 2 points to define a line. Now, we all know that. But I think it's non-obvious what you should do if you haven't heard of least squares. I mean, if you haven't heard of all these methods, how you should deal with this. And the person that invented, there's this sort of priority argument over least squares, but I think there's a more important figure in this discussion than any of the people doing least squares, who I personally believe is Laplace, and I think there are others perhaps that were involved, but Laplace is very interesting on this. Because, of course, the problem is you've got 3 different lines that can fit that data now, and of course, as you increase the data, then you're going to get many more different lines. And it wasn't obvious at the outset, that you should just minimize the squared error, right? What people even said is that you should do things like you should find which of these points is wrong, get rid of them, and keep the ones that are right. So they tried things like fitting all the possible solutions, and then tried to find things like the median. They developed notions, this is in a parameter space, of a sort of median, and tried to select the one that was in amongst the solutions. Partially because they actually didn't have a sense that averaging things reduced noise. That wasn't even a sort of intuitive thing at the time, that if you average stuff, then you reduce noise. I don't think it was of my understanding. And you could read Stigler on this. Stephen Stigler's the very interesting source on this, very readable as well. So what do you do in this case? Well, of course, the problem is that you've got 3 simultaneous equations and 2 unknowns, which we know, like from, again, I don't know how old we were, 13. Probably varies country to country. And you can't solve these for any particular aspect. And I think it's really important to understand what this gentleman, Pierre-Simon Laplace, did. So he, I think his thinking is amazing. I mean, you can actually, I can't really read French that well, but you can sort of read his papers in French. Apparently, if you do read French, it sounds very archaic. But since I don't read French that well, I don't notice. But this is him writing on his philosophical essay on probabilities. And this is the famous thing that he says, which you can't quite see, so I'll sort of read it out. Is, nous devons donc envisager l'état présent de l'univers comme le fait de son état antérieur. And like I always do, I actually have it in English too. Because Nicolas cries when I speak French. We ought then to regard the present state of the universe as the effect of its anterior state, and the cause of the one which is to follow. Given for one instance an intelligence which could comprehend the forces by which nature is animated and the respective situation of the beings who compose it, an intelligence sufficiently vast to submit these data to analysis, it would embrace in the same formula the movements of the greatest bodies of the universe and those of the lightest atom. For it, nothing would be uncertain, and the future as the past would be present in its eyes. And then it goes on to say something about the human mind being something like this. To me, that is one of the most beautiful statements ever made, and for reasons beyond just what's in the statement. So he's saying we should regard the present state of the universe as the effect of its anterior state, which is kind of like the Markov property, right? And the cause of the one which is to follow. Given for one instance an intelligence which could comprehend all the forces by which nature is animated, that's the model. And the respective situations of the beings who compose it, that's the data. Well, I think the données, as you'd say in French, the givens. An intelligence sufficiently vast to submit these data to analysis. So he goes beyond my equation and talks about the computational issue, because it has to be a vast intelligence to do the compute. It would embrace in the same formula the movements of the greatest body of the universe and those of the lightest atom. For it, nothing would be uncertain, the future is the past, be present in its eyes. So if you have the model and you have the data, then you can predict everything. And that, to me, is more fundamental than, that's the fundamental basis of artificial intelligence as well. Like, if you could do that, then you can make all predictions, and once you've got predictions, you can do anything you like. But, of course, the funny thing about this is associated with Laplace, and it's called Laplace's demon. And people even talk about Laplace as if he was an idiot, because it leads to the clockwork universe and the deterministic view of the universe, which is very much a view that people took in terms of trying to find prediction. Of course, ironically, Laplace is writing this in a philosophical essay on probabilities. Probabilities. So this is a straw man. He's setting this up on page 4 of this English translation, to say, oh, well, look, if you had all these things, then you'd be fine. You could predict everything. And still, it seems to me, 80% of the people follow that. And the other 20% say, oh, no, you don't believe in deterministic. Laplace's demon, that was wrong. Of course, he goes on to say, particularly this bit here, this is page 6. This is 2 pages later. It always helps to read on a little bit. The curve described by a simple molecule of air or vapor is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. So what Laplace is saying here is, okay, right, I can do planets probably deterministically. They seem to run around in a very nice way. Everyone at the time believed that was a sort of perhaps infinite, going on ad infinitum. But if we went down to by the way, molecules, I mean, it's funny that they use this term, right? Because, of course, Boltzmann, I think, committed suicide, didn't he? And one of the reasons he had a very unfulfilled time was because no one believed his particle model of air. And that's like, I don't know, about 100 years after this or something. So it's funny, I don't know, you have to be a bit careful maybe in over-interpreting these statements, because it wasn't that he knew that air was made of molecules. But he seemed to think it was. And of course, when you look at things with modern eyes, you can interpret extra things on top of them. But regardless of that, let's do that anyway. And the only difference is that which comes from our ignorance. Probability is relative, in part to this ignorance, in part to our knowledge. So that's what Laplace says about it. And then he doesn't just say things about it, he does things about it. So this is what Laplace's proposal was for solving this problem, which is to introduce what one might think of today as slack variables. And of course they're always there, and if I write it like this, it does make it kind of obvious what's going on. But I think we forget that this is how we deal with these things. And if you think about this being the way you deal with things, then it becomes more obvious how you deal with other uncertainties as well. I don't really like the term Bayesian. In fact, I really dislike the term Bayesian, partially because Bayes' paper isn't very clear and that Laplace did a lot more on it, and partially because the earliest people to do these sort of things just naturally used probability to do these forms of inference. There are very good reasons why Fisher and people like that were against it, why there was a frequentist movement. But I think Bayesian is designed as a term by Fisher to make it sound like a religion. And it's not a religion, it's just the calculus of uncertainties, right? You can have other beliefs. You don't have to have beliefs about whether probability is a rigorous way of dealing with uncertainty. That's fine. The belief issue is where you put your uncertainty. And for a frequentist, putting the uncertainty here turns out to be uncontroversial. So what he did is he said, well, I'm going to introduced this snack variable, but I now have as many variables as I have data. And so now I'm going to deal with that with a probability density. I'm going to say this is sampled from a probability density. So the thing why we don't call that, in fact, he invented the Gaussian density. Also, de Moivre invented it independently, but Laplace invented the Gaussian density. And even Gauss refers to Laplace when he talks about the Gaussian density. He didn't use it here, though. He invented it for doing Bayesian inference, for doing the Laplace approximation on coin tosses. But he didn't use it here because he was trying to look from first principles for the best distribution to use. And he had like some maximum entropy-like principle of trying to get something very, very heavy-tailed. And he would come up with very, very complex densities, and the algorithms to fit these densities were very, very hard. So the reason we refer to it as the Gaussian density is because Gauss took this idea and put the Gaussian distribution on it, which wasn't called the Gaussian distribution. And as I said, he credits it to Laplace, which is why we now call it the Gaussian density. But it's Laplace that invented that density, and it's Laplace that sort of described or did a lot of work. I don't know if he was the first to, but he did a lot of work on this type of problem. So Laplace's idea is to sort of set the mean of the Gaussian to be a function. In this case, mx plus c. And then have a variance in effect. So this is what this implies. This here says that I'm adding Gaussian noise to my function. Well, the top thing does. And this is how you write that probabilistically. You've got your observations minus your function. You're saying this is your distribution. And then you can do maximum likelihood on that distribution to find the parameters of the function. So this sort of gives us a noisy function, and it's not really a stochastic process yet, but it's sort of getting there. But it's a function that isn't, I don't know, it's not a stochastic process so much. It's got elements of a stochastic process if you look at the whole thing. Y is now clearly a random function versus the inputs, but it's sort of random in an uninteresting way. It's independent noise. So this is the point, so I should have made that clear, that what Laplace looked at here was he talked about independence across these elements. Of course, in practice, you don't need to make these independent, and something you'll see a lot in spatial statistics is correlation, spatial correlation between these, and that is typically, they use a Gaussian process for making that spatial correlation, but they have simpler linear models here because they want the interpretability of a linear model. Okay, so should I pause there and just see if there's any questions or anything? No? All right. Nothing too, just like stuff at the moment, isn't it? Nothing too complex, just background. Okay. Okay, but then I think this is where it gets interesting. So what about if you have two unknowns and one observation? Of course, the interesting thing is the last thing was an overdetermined system. This is now an undetermined system. But this is, so we can compute one given the other. So we can do things like, if we've got one data point, if I wanted to fit a linear model, if I knew a value for c, so in this case c is 3 point something, then that gives me a value for m. So for different values of c, I've got no noise here, obviously. I've got different values of m that come out. Now the interesting thing about this is, in the underdetermined system, well, in the overdetermined system, what we actually did was we introduced a probability distribution for a new variable epsilon I. So what we actually did is we made the system underdetermined. We added variables, which was a noise value, which was added in every single data point. So we added like n variables if n was our number of data. So we made the system underdetermined, but then we dealt with that by integrating over the undeterminedness, which gives us that simple, so it's not a very complex integration to get rid of it, but this is the result of integrating out the epsilons, right? Which is the Bayesian process. It's just a very simple integration, so you don't think of it like that way. So you're integrating out your noise, and then this is the formula you get. Conceptually, it's important what's going on here, because conceptually, if you are a frequentist, you will be happy with the idea that you do this, because you will say, this is my model of the real world, and this has deterministic parameters associated. This, you're going to say, is, I like to think of it as the way that the world departs from your actual model. So this is your abstraction of the real world, and then this is your the way you're trying to account for the fact that the real world isn't like that by adding some corruption. Now the corruption in the case of Laplace and looking at the sky was actually trying to remove sort of noise coming from like the atmosphere, little measurement noise, right? Actually, I plotted some measurements that they took, and they were really accurate. There's very little noise on them, very little. Okay, so for the underdetermined system, you can introduce maybe a probability distribution for the parameter c. So that's what we just looked at, is saying, oh, well, what if I sample c? So always, my instinct is that's known. Now, why is that known as the Bayesian treatment? It's known as the Bayesian treatment because we've decided to put a probability distribution on a parameter of our model that a classical statistician would not do, because they're trying to get, they believe that parameter is fixed. They don't believe it comes from a sort of a distribution. But I think that it's all overblown, and I don't see the problem. It's as soon as you introduce a model, you're being subjective. Classical statistics tries to avoid being subjective, right? And I think that that's all you have to remember. So a lot of the reasons why I think that the argument is much better summarized by Fisher was concerned about the subjectivity of the Bayesian approach because you tended to introduce probability distributions over parameters. And he was much more interested in things like randomization and things that he could show were working regardless of the assumptions on the underlying data. And that was fine. That was fine 100 years ago. Unfortunately, as things get more and more complex, it seems, particularly today, as you get less control over how the data is being generated. So remember, in those days, a statistical sample was often collected by someone actually rigorously going around and collecting data. It was a very expensive process. Whereas today, a lot of the data we're getting is biased and has all sorts of problems. So you actually have to start getting explicit about how you introduce those issues. So in Bayesian inference, the sort of thing that people don't like, which I think is a bit weird, is the fact that you have to introduce a prior. I think it's odd that they don't like this because it's not that you're introducing a prior, it's that you're building a model. Your prior combines with your likelihood, actually, and the whole thing is a model. I don't see any difference between that and defining your likelihood. To me, it's just the same. It's not an additional thing you have to do, because if people say, oh, well, I've got my likelihood, and now I have to come up with a prior, and oh, that's such a fact. Well, where did your likelihood come from? And if you think like that, if you think they're separate, you're doing the wrong thing, because there's certain classes where you can definitely, it's not clear where you're putting your assumptions, whether you're putting them in your likelihood or your prior. So a classic one would be things like logistic regression, where there's a specific assumption about the link function. The link function effectively goes around the distribution over the parameters and totally changes the nature of that distribution. And the selection of your link function cannot be done independently from your prior. The two go together, because the whole thing's a model if you're going to use a link function or prior. If you're doing the classical statistic way, you just think about the prior. So you're only ever, to my mind, choosing one thing. Choosing the prior and the likelihood is just one way of building what I think you're interested in, or what I'm interested in, a probabilistic model of your data. A probabilistic model which allows us to interrogate the data. But just to review the process of finding what that parameter is, now again, I seem like I'm really anti-Bayes because I think it's absurd that this equation has a name. It's just the product rule of probability, right, with division. So it's Bayes' rule, but what's going on is this: if you put this up here, Pc given y times P of y is equal to Py given C times P of C. So it's just the product rule equating the two different ways of writing the joint distribution and then dividing by P of y. Now, its implications are very important. So spotting its implications are very important, because what it's saying is if I represent my information about a parameter C at this stage, before I see data, then what Bayes' rule gives me is my belief in the parameter after seeing the data, the posterior. This is the prior, this is the posterior. So that conception is super important. And that's, Bayes writes about it, but I think that the forward Price, I think is it Richard Price? Who writes the forward, is the person who's most lucid about why that's important. And it's just the way also, it also allows you to swap the conditioning, various other things. So it's Bayes' rule, but it's just the product rule. And it went through this weird period where it was considered like mystical, like you can read press articles, And it even makes it's like in the 10 greatest equations or something like that, along with some really difficult equations. like the wave equation and stuff like that. I don't understand those equations. I understand this one. This one's easy. Doesn't mean it's not. I mean, it is important, but I just think probability is important, right? It's just a consequence of probability being important. So this is the sort of thing that goes on. You start with a prior belief about a parameter c. For some reason, I've put it non-zero. You would normally start it with 0, perhaps. But here I put it non-zero. And then the thing I like to show is what happens is I'm plotting the likelihood on the same scale. Now, this is an odd characteristic of Gaussians, another odd characteristic, that the likelihood is, if a Gaussian likelihood P of y given m, the form of the function, it's a likelihood function, it's not a distribution, happens to be Gaussian, right? And happens to look like a Gaussian, just because y and mx plus c appear together, because it's representing the mean symmetrically. So it looks like it's also, this is c here, this is over here, sorry, I should have this axis labeled c, this is the prior over c. This is a function of c that happens to, because of the way things are, I can't go that far back I think, because of the way things are set up, happens to look like a Gaussian form. Now normally, many likelihoods would not look like densities. I shouldn't say distributions really, should I? I should say densities. These are probability densities in these spaces. So most likelihoods would not look like densities, but the Gaussian likelihood happens to. And then what do we do? So I mean, Bayes' theorem is actually conceptually quite simple. We've got our prior that is saying, okay, things don't happen down here, things don't happen down here, things happen in here. And then all you're doing is multiplying the two, the prior times the likelihood, which gives us this region here. So it's basically an argument between the prior and the likelihood about what's coming. So the prior is coming from the model, is the way I conceptually think about it, and the likelihood's coming from the data. And all you're doing is saying, well, we'll believe in places where both agree. But of course, if you just multiply them together, that can't be the posterior because it's not normalized. It can't be a distribution over C. So the other term in Bayes' rule is the normalization. Likelihood times prior. Note likelihood is not a distribution over C, a density over C. It's a function of C. Probability notation is not the same as functional notation, by the way. For example, you can flip if it's a joint distribution, P of y comma C is equal to P of C comma y. It's not a function, it's different notation. But here, when I always think if some people put parameters of the distribution under here. I don't, I never do that. I always put the parameters of the distribution on the right, because they're conditioned on those parameters. So here C is a parameter of the distribution, and here C is the variable over which you're placing the density. So in order to achieve that, you have to normalize, and that's the difficult bit very often in Bayesian inference, is you've got to compute the normalization factor, which requires integrating out C. So the integration is the typical part in Bayesian inference for most people. And if you do that, then this is what you get. You get an updated posterior, and I've written this complex little bit of math to show what that posterior form is in terms of these other examples. So that's your update once you've seen the data points. So you get a new distribution of the values for C. Now that's great, but very quickly, okay, the reason why it also works very nicely is because of this characteristic of the Gaussian. So it's an exponentiated quadratic, and the prior is of the form of e to the something squared. The posterior, the likelihood is of the form e to the something squared. So when you multiply them together, then you just get a sum of those two coming up the top there. So the result is of the form e to the something squared, because this is also a quadratic form. And you just complete the square to resolve what that thing is. You actually, when you do these things with Gaussians, you can just recognize that's exponential quadratic, that's exponential quadratic, that will be 2. The normalized exponentiated quadratic is the Gaussian density. So you know immediately that that's going to be Gaussian. So that's an odd characteristic. Most densities aren't like that. Most likelihood priors. So there's a thing called conjugacy, where the form of the prior, the functional form of the prior matches the functional form of the posterior, given certain likelihoods. This goes beyond conjugacy, because the likelihood of Gaussian, the prior is Gaussian, and the result is Gaussian. And it's unusual. Most things, you multiply them together, even if they're in the same class, don't lead to a function that's in the same class, a distributed density that's in the same class. Okay, so now I'm going to skip. We've done Bayesian inference over one parameter. I've justified it at length because I kind of, from my memory, no one ever did that to me. Maybe I missed the course or something, but I like to sort of go through it. So, but what I'm going to try and do is I'm going to rush through the We're going to go from univariate to infinivariate. You know, why stop at multivariate? But no, we'll do a little bit on multivariate. So of course, actually, a linear regression, normally we go y is w transpose x plus epsilon, where I'm always going to use this notation, this inner product notation, instead of this sum notation. The amazing thing about a lot of the work done by sort of Laplace and all these others is they didn't have linear algebra. It's exhausting looking and thinking about what they must have done when they used this notation. Linear algebra makes everything so much easy. And it only comes in matrices, I think, in the 1930s, which is shocking. Really shocking. Imagine, you know, the same. And I think it comes in the study of the determinant of the matrix, not so much the matrix multiplication. But you're going to see how easy matrix multiplication makes everything in a little bit. So we dropped C here for convenience. Normally you have an offset. So this is like mx, but it's a multivariate m, and we've flipped m upside down because in neural network world we like to use w's, and that's sort of infected the whole of machine learning. A long time ago, in the first wave of neural networks. So in stats, you would use beta here. And I think that's actually quite useful because I think if I use beta, it means I would care about the parameter. So I'm going to use the parameter later. I mean, it means I think the parameter is meaningful for me. If I use w, it means I don't care. I'm just using the parameter to construct a model, and I don't care so much about the parameter. So when you see someone using beta, they'll treat beta in a very different way to the way we'll sort of treat w here, because they'll try and prove things about beta later on. In machine learning, we never go that far. So to do this, you need a prior over w, which needs a multivariate density. So, okay, we need a multivariate Gaussian prior. So this is now the form we end up, I mean, this is just Bayesian linear regression. So you end up with the minus f of x here, and we need a multivariate prior over w to deal with that. So this gets more complicated, but it's just linear algebra. You can do the whole thing analytically. I mean, this is like we've now in one, if you think I'm going slow, I've done the first 10 lectures of my master's course just now. I do more stuff in between. Not the first 10. I'm about to do the first 10. Okay, so we need to go multivariate. And I'd just like to introduce this conception of what multivariate looks like for the Gaussian, because I just think having an intuition about how these things feel is really important if you're going to either work with these or develop these algorithms. So multivariate, so let's, I have a multivariate distribution, which is my height and my weight. I can jointly look at them. And here I'm just showing you what we call the marginal distribution of height and weight, right? So this is the distribution over height. I'm up here. This distribution of weight. I'm probably creeping up here. Not too bad. So I'm matching. Okay, but what if I sample from those distributions independently? So here I've taken one sample from the height, so it's turned out to be an average height person, and one sample from the weight, so it's turned out to be a sort of light person, so it's come down here. This is the weight on this axis, this is the height on this axis. So we've got this sample here. So independent samples, I can just do this separately from these two Gaussians for a number of values. So I've now got a sort of tall person, a heavy average height person, and now I've got a sort of, I don't seem to be getting much variation so far in terms of height. That's just coincidence. A little bit of variation now, but I can sample from that to my heart's content. That's what we can think of as a multivariate density, right? So when I'm doing that, and I'll do this in a moment. The reason to plot this is to get used to this view of the thing. I'm showing you a contour on a hill. It's beautiful to be in Sheffield with hills. There's a hill over there, if you can see it with the... there's no hills. There's one hill in Cambridge, Castle Hill. So this ellipse here is the contour at a distance which is one standard deviation away from the mean, which I've marked with a cross. So I'm going to use that to represent Gaussians in 2 dimensions when I do it, that illustration. But the thing about that is it's not very interesting because these two are independent. So this is a classical sort of probability formula that if you've got independence, then the joint distribution can be decomposed into the probability of the height times the probability of weight. Now, of course, in reality, they're dependent. I mean, this is a weird index. This index, I think, is due to Quetelet, I think, who is an amazing person who did like all the early work on statistics, like came up with the concept of the average man, we'd say the average person today, and this sort of thing. All this work was done by Quetelet. I think he was from Belgium. Looking at the statisticians, see if they frown. Oh, they don't know. Good. He was from Belgium. And he worked on, he was interested in like how you could take mathematical methods and apply them to society. And he did a lot of the early work on statistics, but it was before mathematical statistics. So he didn't do a lot to prove things about the numbers he was coming up with, which is what leads to this concept of lies, damn lies in statistics, which is then corrected by mathematical statistics around the time of Fisher. I think with big data, we're in the lies, damn lies, and big data era at the moment. So we need to sort of put the same thinking in it. So anyway, I think Quetelet came up with the body mass index, which is odd from a physicist's perspective because this is weird to divide a mass by the square of the height. So people have other things that they recommend, but everyone uses that, right? And that's saying there's a correlation. Now, I can't represent that correlation because it's nonlinear with a Gaussian, but I'm trying to represent it here, where what I've done is conceptually, you can think of the idea that, think of some axes here. I've effectively rotated this ellipse. And we'll look at that mathematically in a moment. But basically, that gives us a correlation between the two. And now I can't sample them independently. I have to sample them together. In fact, what you do to do have people here done multivariate samples directly from having to do that? What you do when you do that is you sample independently, and then you use either the Cholesky decomposition, or it was the typical way, but conceptually here, the way I'm talking about it, if you use the eigenvalue decomposition, you would assume one of those samples is there and one of those samples is there, and then rotate by the eigenvectors. So conceptually, that's how you get samples from multivariate Gaussian. It's more efficient to do it by Cholesky, but that's less easy to talk about what that means on a picture. Here, every time I take a sample, I can't sample independently. The independent samples are rotated around. So the multivariate Gaussian, to me, exists as independent Gaussians that have been rotated. This isn't true for other distributions, by the way. That's why ICA exists, because other distributions don't stay in the same class when you multiply them together. So the reason this works is because you multiply two Gaussians together and they stay in the same class of distribution. Because two exponentially quadratics, we're not doing prior and likelihood, come out with the same joint distribution. So it keeps working, this multiplication thing, and then the sum thing. These are just amazing sort of things about Gaussians. So the independent Gaussians, you would write them like this. So if you just take the product, that's what's happened. I've multiplied the probability of weight times the probability of height, and I've got the sum appearing here, and then these things just stay as out the front as a multiplication. Conceptually, what I then like to do is write that in linear algebraically. So I've introduced a diagonal matrix of the variances, a column vector of the means, and a column vector of W and H. And I'm just going to rename that Y, W and H, and the means a mu vector, and D is a diagonal vector. Now that thing on the left, the determinant of a diagonal is the product of the diagonal elements. So I'm replacing sigma 1 times sigma 2 with the determinant. Yeah? And now you can see the multivariate Gaussian forming. That's independent, but if I introduce that rotation, it could be a permutation as well, into this thing. So I rotate that input space, put the rotation there, rotate the input y, rotate the mu. And I don't have to apply it here because rotating a determinant, I can rotate these, no, I don't even need to apply it yet there, sorry, ignore it, forget I'm saying that. Now I can pull that R out. Now the determinant of C inverse, well the determinant of C, where C is R, D, R transpose, is equal to the determinant of D because these are rotation matrices. That's a property of determinants. They don't vary under rotation and permutation. But what I've got now is I pull the R out and I have this object here which is the covariance matrix, which is exactly, that's actually the eigenvalue decomposition of the covariance matrix, right? So that's actually the principal components of the covariance matrix. But I think that that's, people think of the covariance first and the principal components the other way around. I actually think that thinking about the principal components is a key point. Okay, so we've got sort of already these rotated covariances. Okay, but now the important bit from what happens to these multivariate things. So as we said before, the sum of Gaussian variables is also Gaussian. And scaling a Gaussian leads to a Gaussian. Now this becomes really interesting as we start applying linear algebra to these objects. So if we have, in the multivariate case, if we say x is sampled from a multivariate Gaussian with a mean vector mu and a covariance vector sigma, and then we just say y is equal to wx, I could make an add. If I add something here, then it just adds to the result, so I'm just ignoring the adding. The multiplication seems important. Right, a matrix multiplication is just a product of that vector. So the top row times the column, multiply all those elements and then sum them together. Right? So it's just scaling followed by sums of Gaussian distributed entities. And as a result, all that stuff from before follows through. So as you might expect, the mean of mu is scaled. In fact, I just did this with R on the independent data. The mean of mu is given by wx, w mu. And then here, that's the interesting point. And it's sort of obvious once you have this concept of underlying this thing is this sort of sigma squared. Well, it's not obvious, but it's intuitive. I mean, before we multiply by r, but let's just put the sigma squared here, like that. You can sort of see that you're therefore multiplying w times sigma, sigma, times sigma, sigma, times w. And since these are standard deviations, they're existing in the same scale as w. Of course, the square, the variances, end up with a pair of these things around to manipulate the thing. Now that turns out to be critical, because it turns out that what we're doing here is very sophisticated Bayesian inference. If this was a prior over x, and then this is a multivariate likelihood, right? So this is the prior over x. This is the likelihood which is saying y is equal to wx. We've not put noise in for the moment. Then this is the marginal for y. So what this little thing here does in very easy terms, which look much more like classical maths, don't require much probability, is saying, well, let me not wipe that off. Is we would normally write p of x, p of y given x, comma w, p of y given, what am I integrating out? W. This is actually PCA, principal component analysis. So if I set sigma to be equal to I, and I'm going to take mu to be equal to 0 in that latent space, then what this gives me is that this p of y given w is directly equal to a Gaussian with 0 mean ww transpose as the covariance. And that's actually what Hotelling writes down as PCA, where he has x as a q-dimensional and y as a p-dimensional. So w is a p by q, so this is a p by p, but it's low rank. It's a degenerate Gaussian form. And probabilistic PCA says, oh, let me do this complex thing of adding a noise vector to that. So that's a vector, the same length as that, vector matrix. And then if I then say that epsilon is drawn from a Gaussian with 0 mean variance sigma squared I, then I'm adding that. Covariances add together, right? Remember, that's another property of Gaussians. So the end result is that instead. And that's called probabilistic PCA. And if you make that diagonal, let's call it delta because we've used d, then you just get a delta here, and that's called factor analysis. All derived very quickly from one equation. Of course, the equation doesn't give you something else you're interested in, which is the posterior over x, which would be p of x given y. Right? So it's a very, very important relationship. It looks simple, as you like, but people just don't use it. I mean, and maybe they do now. I don't think I was ever taught it that explicitly. I ended up doing the integration lots and lots of times and then realizing later that this allows you to do it all very simply. Okay. So that's the sort of, we're going to move for the last 25 minutes onto infinite dimensional. So I've sort of tried to go slowly on the concepts that the way I see the Gaussian. But what we're going to do is sort of now make this big jump from multivariate to this infinite dimensional object. So as a sort of why do Gaussian processes appeal to me? Because I believe that the world would be an amazing place if the state was jointly Gaussian, because then we could predict everything. And there was a time when this occurred, apparently. I'm not an expert on it, but Kyle Kremner was confirming that it's the case. So does anyone know when the world was jointly Gaussian? I'm not a cosmologist, but the world was jointly Gaussian. So the world was jointly Gaussian at the, as it transformed from plasma to what we see today. So the cosmic microwave background is a Gaussian process, and its parameters apparently are like the 6 fundamental parameters of the universe, including like dark matter. And one of the things they're trying to do is understand more. That's why they try and get better measurements of it. But interestingly, the thing about it is the temperature is many billions or something, and the variance on that process is very, very small compared to the overall temperature. So it's very, very hot plasma, but the movement, the variation inside there was Gaussian. Of course, the air around us is Gaussian today. Now, it's kind of lucky that the universe isn't still Gaussian, because we wouldn't be here to talk about it. But what we apparently see is, or conceptually you can think of that initial Gaussian latent process going through many nonlinear functions to be non-Gaussian. That's what we see today. That's called a deep Gaussian process. But anyway. How do we do that? How do we have a jointly Gaussian thing? So in that case, the cosmic microwave background, let's see if we can just get a picture of it in case that's interesting. Oh, maybe I won't. Oh dear. Control. No, let's not do it. Let's not do it now. We can look at it later. So what we want to do is have that's a spatial function, the cosmic microwave background. So it's a sort of temperature value at different points in the sky, and we want those points to sort of be correlated with each other. Now what we're going to do to introduce that is that we're going to think about a multivariate Gaussian. So I just spent a long time introducing multivariate Gaussian, but I introduced 2-dimensional. But we're going to talk about a 25-dimensional. So we've got correlations now over a 25-dimensional Gaussian. And I'm visualizing the covariance of that Gaussian. It's 25-dimensional in this plot here. This yellow is 0, and the sort of sky blue is cyan. Now, what's going on here is I'm showing how strong the covariance is between any 2 points. So here it's 0, and here it's actually 1. Now I'm going to take one sample, but there's 25 dimensions in this, so I'm going to take one sample from this 25-dimensional Gaussian. It's not 25 samples, there's going to be 25 points because it's 25-dimensional, it's one sample. And that's what it looks like. 25 dimensions, each plotted along their index. Now the ordering of this, I could order this any way I like, there's no rules about how I order it, but I've chosen to order it such that it's banded like this, such that neighboring points are highly correlated. So if I take 2 points on there, these 2 points correlated here, and they're so strongly correlated I can't see the difference in colors. When I had this in red, I could see the difference in colors. I moved to cyan because I'm slightly colorblind, but apparently it's even worse. So this is the covariance of these 2 points here. Now that's another remarkable property of the Gaussian. Okay, that's odd, right? Because what we just did is a massive integration. And it must be true, right? Because if we were to turn this matrix W, when we had the W thing before, into a selector matrix that was just selecting 2 points, right? So why is this true? Because the properties from before, if W were to just be selecting, if W were to just be mostly zeros, but then selecting a couple of points, 1, 1 at the top and 0 everywhere else, then we would just get out the top quadrant here, yeah? Now that means that we're integrating out every other value, 25, 24, 23, 24, down to 3, to look at the marginal distribution of F1 and F2. Okay? The marginal distribution is what we're after. Because I want to look at the marginal distribution of this joint. Because I want to explore that marginal distribution of F1 and F2, because I can't explore a 25-dimensional space on the board. I can only do 2. But we'll do it with different things as well. So that's an interesting property, that if we want the covariance of those 2, the joint distribution of those 2, then we're looking at this joint distribution and these points here, but we're integrating out to look at just these two. And this is the covariance. So it's very highly correlated. So this is 0.986 and 1. So the correlation, because the diagonal is 1, so I've removed the colors and shown you the numbers. Because the diagonal is 1, this is actually not just a covariance, it's a correlation. So it's a correlation coefficient of 0.98. Very, very strongly correlated. But then we can look at the equivalent Gaussian that we've been showing before, this rotated Gaussian. But what you see is it's very, very narrow for this strongly correlated example. Now, what I want to be able to do, I've got a joint model over F1 to F25. Imagine F1 to F25 is all the things I need to know in the universe, all 25 of them. If I've got a joint distribution over all 25 things, I can ask about any one thing given anything else. So I can ask the question, what's the value of F1 given F5? Right? I can ask, what's the value of F3 given F2 and F7? Now that's, to me, the way we'd love to. I mean, it's the right way of doing, of answering questions. You have a probabilistic model that's joint over everything, and then you get a distribution you can condition on anything. The reason we don't do it in practice, it's very hard to do the conditioning, because you do a lot of integrals in there. So because of that, we don't normally do it, but with Gaussians we can, which is why it's very elegant. And it's why the way of doing stuff with Gaussian processes is so unlike other methods, because it's the right way, but you normally can't do it. It just happens you can do it because of the tractability of Gaussians. So what I might want to know is, so going back to these points here, so F1 is down here, some negative value. Let's say I don't know F2. All I know is F1 and this joint covariance. I can ask the question, what is the value of F2 likely to be given F1? And that's known as conditioning in probability. So here I've drawn a line across F1 at the actual value observed of F1. And the conditional is this. F2 given F1 is a Gaussian. It's quite highly peaked, because the way conceptually you can think about this is like, okay, marginally, if we were to look down here, the marginal of these Gaussians is actually variance 1, right? Because the marginal of any of those must also get rid of that, right? So it's variance 1. So marginally, we look at the standard deviations here, they line up with the axes. So the marginal is actually a sort of a Gaussian like that. So when we look over that hill there, there's a hill there. If that was a two-dimensional Gaussian distribution, and this is one of the axes, we're looking at the marginal distribution, right? Now, if we wanted the conditional, we'd have to get an enormous saw and cut through that hill along one of the axes, and then look at the profile. Maybe we could do this by some more clever way, but and then look at the profile of the hill there, and that would give us the conditional. But once we got it, we'd have to renormalize, right? So it's not just the sort of, as you cut through the hill, the outline of the hill does, it's renormalize that afterwards to make sure it's a probability distribution, okay? So that's giving me the probability of F2 given F1. That's learning. I knew I had a model of F1 and F2. I observed data F2, condition on F2, sorry, I observed data F1, condition on F1, I make a prediction of F2, right? And it's a narrow prediction. It's saying, oh yeah, because of the strong correlation. Notice it's not totally tight. It's as these correlations approach, it will go down to a delta function. If this was 1, this would be a delta function. But you might expect it would be really tight. It's not that tight. But it's saying, yeah, well, look, in all likelihood, you'll certainly be in the same half space. It's likely to be a negative value for F2. If we look back at the actual value for F2 that we did sample, initially from the joint, I sampled that from the joint, we also see it's negative and it's actually gone down a bit. But it could have gone up, it could have been anywhere around here, given this covariance. So that's what the Gaussian is telling us. The covariance is telling us. It's telling us how these things vary up and down as we move away. This covariance. I didn't say where the covariances come from. You might know, where did you get that? It's the model, actually. So if you have a way of writing down a covariance between different objects, you can do this, but it kind of becomes important where the covariance comes from. Okay, so that was the actual value for F. I've now plotted F1 against F2 on this line. So, obviously it comes from somewhere under the density. Now, of course, conceptually, that when you're sampling the whole function, in order to sample f3, once you've got f1 and f2, you can look at f3 given f1, but you'd have to look at f1 and f2 to get the right prediction for here. You'd have to condition on f1 and f2 because you got them both. And you could actually chunk around here doing that, and that's what you do in a Kalman filter looking ahead. Here, this isn't necessarily time, this is just a sort of function. Okay, so let's look at f1 and f5. So predicting f1 and f5, well now, sorry, that should be updated. I think the correlation between these two is about 0.56 now. I don't know what, I've lost the, that's not the right number. So the correlation is something about 0.5 or 0.6, and now I get a much more diffuse Gaussian. So actually a large section of it thinks it could be positive. So it's actually not sure that it's in the negative space. Even with that reasonable correlation, things are pretty loose. It actually is negative in this case, and that's very nice. So, but where did that let me pause there actually, because I just want to emphasize what I'm trying to do here. So this is over f, which is a function, and the reason I'm doing it over f is because I tend to use f to be the thing I put the Gaussian process over, and then I tend to corrupt it to see what I observe, which is y. So I might add Gaussian noise, but I might do some other likelihood I'm interested in. So I tend to think of putting the priors over functions. But so far this is just a discrete world, right? And one important thing that I went through as we did this was that we could integrate out all these 25 things, and it didn't affect the joint distribution of these two. That's very, very unusual. So normally if you have a joint distribution over things and you integrate over them, it changes the form of the distribution you've got. So think about, anything like to do with Boltzmann machines or something like that. As soon as you introduce hidden variables into those models, they become way, way more complex and they go into a different family of variables. Because it's not normally the case, or think about Gaussian mixture models. As soon as you do a Gaussian mixture model, you've got a joint distribution which is selecting a Gaussian condition and an observation variable, and as you sum over them, you get this mixture of Gaussians. You change the class of distribution when you marginalize, when you integrate out variables. Here you're staying in the same class of distributions. So conceptually, all this stuff could have been for 25,000 points. Not just 25. It could be for countably infinite points. And in effect, that's all you need to know if you're just playing with Gaussian processes at the level I play with them. There's lots of theory on measure theory and everything else that talks about how you go to non-countably infinites and put distributions over that. But the starting point, I don't ever have to deal with non-countably infinite myself, so I don't even have to deal with countably infinite normally, but conceptually, because I know that there could be, I don't have to worry about what variables haven't yet been mentioned when I'm doing predictions here. So there could be 29 million variables that no one's ever told me about. But I only have to worry about the ones I've seen because I know I can integrate them out and just focus on the covariance of the ones I'm interested in. That works for the covariance. It does not work for the precision of the Gaussian, which we might talk a little bit about tomorrow, which is why the covariance is such a fundamental object. Covariance isn't always the most intuitive thing to tell you about your process, but it's very fundamental because of this property and because of the fact that if you combine Gaussian processes together, you add the covariances and so on and so forth. So I kind of view, like from a software engineering perspective, the covariance is like the API of the Gaussian process. You have to turn it in, if you want to combine lots of them together and do stuff with it in linear ways, you end up having to represent in the covariance form. If you do Kalman filters, you typically would not represent the thing in the form of you would not write down the full covariance because that would destroy the point in doing the Kalman filters. You tend to work with precision matrices. But if you wanted to combine that Kalman filter with a different Gaussian process, then you would have to map it into the covariance so you could combine them. So the thing we're sort of really, really interested in, say in Sheffield and a lot of other people, is the power you get when you do the covariance representation allows you to combine these models and be very flexible about your modeling. Unfortunately, it comes with the cost that you're representing in forms of the covariance and you've got higher computational complexity. So it's a slightly irritating trade-off. You've got these beautiful modeling sets. For 20 data points, you can do the most amazing things ever. But then someone says, oh, that was great. Could you do 50,000? And then it gets a bit more complicated. That's it's a nice elegant modeling framework if you can do all these things together. Okay. So why does it get complicated? Well, Oh, damn. Sorry, I updated my slides and I missed out a bit. Let me just briefly say why that's complicated by writing it on the board, and then I'm going to stop there because I'm running till 1:30. Is that right? Yeah, good. Okay, so let me just say why that's complicated. I'm not going to talk about the covariance now, which is going to be, maybe Rich will talk a bit about it. But I just put in the slide that somehow I managed to drop when I updated my slides. So the slide that I managed to drop had the details of how this conditioning is done. So we typically think of the Gaussian process. So I haven't said where K comes from, and it's just a Gaussian matrix for the moment, not a process. It'll turn out to be a function of the inputs. Okay, but let's just we don't need it for this little bit of maths. If f a priori is drawn from a Gaussian process, and maybe let's think that f is split. So what we're going to say is f is split into two types. One is data we've seen, and the other is data we've not seen. So I'm representing that with three matrices, because this is just one transpose, because it's symmetric. So this is a covariance, a joint covariance between the training data and the test. Now what we're typically interested in is asking questions about our test data. We tend to use f star for test data in GPs. I don't know why. I think someone did it once and we all copied them. So we're interested, this is learning, or this is inference in a GP. This is the model, K, that it's Gaussian and that the model is K. This is the data, the observations of F. We haven't shown where X comes in yet if it's a regression, so just ignore it. It's actually hidden in K. This is making predictions about future data given existing data. This is a joint distribution. This is simply a conditional distribution. And Gaussian conditioning is what I've been doing here, but in one dimension. Now the point is we can do it in multi-dimensions, and it turns out that this is also Gaussian with a mean given by mu and a covariance given by sigma, and I'll give the form for those in a moment. So this is also Gaussian, but it's a multivariate Gaussian. And so the form of that mean and covariance is important, and these are the sort of, this is learning in Gaussian processes. It's just a couple of linear algebraic operations that mu is equal to k star f. So that's the cross covariance between the test data and the training data, the chunk of that, times k f inverse. So this is the covariance of the training data times the observations f. Now, if that covariance k star f was kff, what would happen? This would be kff times kff inverse, which would just be that mu is equal to f. Okay? Makes sense. Now the covariance is equal to k star star. So that's the prior covariance of f star. But then you lose variance from it as you observe data. So k star f, k f inverse. So that's the same as that bit. K f star. That's the posterior. Okay, in one dimension, what does that mean? It's sometimes easier to think about these as one dimension. So if in this example here, this was 0.98 and that was 1. That's not that example. It's the this example. This is 0.98 and this is 1. So in one dimension, this object is just a scalar. It's 0.98. This object is that object, which is 1. And this object is the observation, which is minus something. So in that case, it would be 0.98 divided by 1 times whatever the value of f was. Let's say it's minus 0.4. So the mean is equal to a little bit less than minus 0.4. There's a bit of regression to the mean, actually. It pulls it back a little bit to the 0. Yeah, because its prior belief is it should come back to 0. So it's pulling it back to 0. Not all covariances do that. Other covariances will do other things according to what other data has come up. You don't always pull back to 0. And in fact, even in the RBF, you won't always pull back to 0. But here it's pulling back to 0. And then the variance of this thing is going to be 1, which is this element here, minus 0.98 divided by 1 times 0.98. So that's a little bit less than 1. That's a square. That's a squared term. So it's 0.98 times 0.98. I don't know, what's that, 0.96? Guessing. So this is 0.04. So the standard deviation would be 0.2? No. 0.0, damn it. Okay, standard deviation would be something. The standard deviation would be this value here. There you go. Now, if in the other case where it's more like 0.5, look how things change. If this is 0.5, then we get 0.5 times minus 0.4. So we're much more shifted into the zero. So the actual mean of this thing is more like minus 0.2. We're shifted in from the, so it's like there. Yeah, something like that. So it's about minus 0.2. And then interestingly, what happens to the variance? Well, this is 1 minus 0.5 times 0.5, which is 1 minus 0.25. So the variance is 0.75. Standard deviation is like 0.8 or something. So, it quite rapidly starts. You can see why you get that effect, that as the correlation decreases, you quite rapidly start to go back towards the prior. And this is quite a large variance there. So normally, when you do actual learning, you've got other things going on, like your inputs in K, and you wouldn't just have one data point. You would have more. Actually, you can do one data point with Gaussian processes. So one thing that people do, and certainly I've done in the past, other people, I think John Platt was one of the first people to talk about doing things like this, was effectively do an enormous amount of work to learn this matrix. I had a paper on this with John Platt a long time ago, from other data, right? So from other data, and then you can use this matrix to work on new data and make predictions around one point. So that's like a multitask learning thing. So people do data sets with 1 point or 2 points, but normally you have many more. And when you have many more, the challenge is this. First of all, you do this. You don't do this by direct inverse. You don't actually do it. Normally you would think, oh, I should do this by solving this system. So I should solve this system. I shouldn't do the inverse. But actually, because of the determinant in the likelihood, we tend to actually do an approach to doing the inverse, which is the Cholesky decomposition of this. So we do the Cholesky decomposition of this. That gives us the determinant, which appears in the likelihood, which we'll need, and I'm going to talk about tomorrow. And then we combine that with f to make mu, and we also have that same object here. So once we've computed that via Cholesky, you can do the same thing here. But look at the problems, right? This object is n by n, where n is number of your training data. This you can do on the fly, right? Whenever you get tests. So it could be, it's infinite in theory, but you only ever look at what people are asking you about. This object's n by n. Now, so two problems. You've got a Cholesky decomposition on an n by n matrix, which is n cubed in complexity. But in my experience, what tends to happen before you even get there, you can do those. I mean, it's amazing how fast these things can work now. You can do maybe, I don't know, last time I tried it, I think I got up to 40,000 or something. You could do a Cholesky decomposition, takes about a few minutes. But then the thing that happened is I ran out of memory. Because, of course, storage of this thing is quadratic in n. And I think, yeah, it's I don't know if this is generally true, but after that I decided, well, that makes sense. You've always got more time, but you don't always have more space. So it seems the quadratic memory complexity actually often hits you before you even start thinking about doing the cubic. The other problem is, you don't just do this once, because you tend to try and fit the parameters of the covariance function. So you're doing this multiple times inside a loop to do your optimization. And that's the challenge. In practice with Kalman filters, there's ways of doing this more efficiently. In many algorithms, there's ways of doing this more efficiently. But this is the worst case situation, which is the sort of headache with GPUs. And I will stop there and take questions. I should have taken more questions while I was going, or you all understood everything.
So can you just go back to the slide where you plotted the new Gaussian over?
The
next one.
Yeah. Yeah, that one. Yeah.
So, I mean, I think I misunderstood it first, when you went to that. But are you always going to have a summation? You're never going to have any skew?
No.
Because when you've got the joint covariance, I mean, visually, it looks like you might get some skew. Is that never?
Yeah, no, that's never the case, and it's a remarkable sort of thing, that any slice through this hill, like if we slice through that hill, it wouldn't look Gaussian. Any slice through this hill will be Gaussian, which is a very odd property, and it's kind of related to the sum of, because it's like the slice through is like, I don't know, some sort of projection, I think. Yeah, but you're right to highlight it because it's really unusual, and it's kind of the problem with doing this generally. Like if we had, like, so if we existed in the time of the universe with some kind of hot plasma, then we could do all our predictions very accurately. But today, with the universe distributed as it is, very non-Gaussian, even if we knew the distribution, doing this type of conditioning would be awful. It would be extremely computationally intractable, and indeed it is, and which is why you get headaches with complex Bayesian models. But yeah, so you're right, this is very exceptional that conditioning comes out like that.
Intuitively, if you look at that plot, you might think that the distribution was centered on the
Yeah, no, that's right, yeah. There's actually, and there's even a little optical illusion that because of the slant of the thing, it doesn't quite look, you know, but yeah, but it is like that. It's the only distribution, by the way, that when you take independent products of the marginals leads to a circular contour. So independent products. You can have other distributions that have circular contours, but they're not independent across their axes. Or I say axis-aligned ellipse contours it will lead to. It's the only distribution that does that. Yeah. Other questions? The central limit thing, by the way, is also to do with this exponentially quadratic thing, adding together this property of this weird form that combines in lots of different ways. Is that it? That was the only thing. We were all thinking, oh my God, when's he going to get onto something technical? Other people will get more technical quite quickly. Okay.
If you go back to your early meta stuff about statistics, you mentioned that statistics is about turning humans into computers.
Mathematical statistics. Yeah.
So yeah, but the point really was if you consider that this is all about making predictions, I suppose the question is why is that distinction important?
It's very important, actually. It appears that it's not important, but at some point you have to explain the prediction to a human. And statisticians, so we have lots of these meetings, a lot of statisticians come to these meetings, and we often have a post-meeting workshop. And it's very interesting when everyone's doing speculative modeling. So we had speculative modeling about malaria. I think it was Nick Golding who gave the talk. I can't remember if it was Nick. But they had a spatiotemporal model of malaria. But people actually make decisions based on the models they present. And he wouldn't let us record the predictions he was making with his speculative model because hundreds of millions of donations go into distribution of nets on the basis of these predictions. That means you really have to have a good sense of the truth of what's going on. And that's why I think that people will err towards simpler models that make coarser predictions. Of course, in the end, if it's all about prediction, I mean, that's in some sense, so humans themselves are like that. We just run around trying to predict stuff we can't really explain even to ourselves. But if we're communicating with other humans what we found, or if we're trying to summarize data, then we need to present it in a way that the human can interpret. And that needs to be reliable and as objective as possible. And I think that's a really interesting challenge for statistics, is staying objective as the models get more complex. But then machine learning has the same challenge, is that we're making complex predictions about people, and new European legislation will ask for that to be explained. So we all end up worried about the same thing, but I think it's just the starting point is slightly different.
It's about making it tractable for humans in some sense.
Yeah, tractable is probably not the best word there, because that implies like they might be able to do the maths. But I think it's more than that. I think the biggest failing of all of us, the statistics and machine learning and everyone else, is making normal people in the street understanding the consequence of the modeling we're doing. And if we really, and I think stats was more about making professionals understand. So it's about politicians and, or people developing new drugs. It's more about scientists. But you still have a specialist statistician to do the analysis. But we're getting into the world now where, sorry, I'm just going off on one that wasn't really related to the question so much. But the consequences of our predictions affect everyone. And yet people don't understand why it's happening or what's going on or how to control it. Because people don't have a good model for this type of prediction internally. We know what other people are like. So I think that crossing that boundary from the data to the human is vital for data science. And I think stats has worried a lot more about that, perhaps more formally than we're looking at it now, than machine learning has. Other questions? Okay. Right, well, what have we got? We've got coffee. It's normally coffee. Brilliant. There's coffee over there.